Good morning and welcome. Today is, what is it, November 5th. And today we're going to be covering chapter 20. From the get-go, we're supposed to be scheduled for an exam this week, but we did not because we were behind a little. So we're actually 1 week behind in our plan per the syllabus. So here is the deal. We really have to do something. I really don't want to rush the content too, but I may have to shuffle the chapters a little because I think it's important that we get into also the astronomy stuff, namely the solar system and also the stars in the universe. So, and that's toward the end of this class, so we really need to get to them. And the exam 3 is going to be on a week from today, so Thursday next week. Again, similar to what we did exam 2, it should be available the evening before and running into the class time, which means that by next week you will have, basically you will be working on the exam. Now, that means that we're not going to be actually meeting on that day, which means we're going to miss another class too. So we really have to work on probably condensing a couple of these chapters from Earth Science into one, and then moving along. I think we wasted a little bit of time when we were doing a lot of this stuff in chemistry that probably we're not going to need a lot of it in here, but hopefully you guys took something out of it. Okay, so and that also because we also had to lose another day for the exam 2, I guess, too. Okay. So again, for those, before you guys ask the question, there will be the review again, hopefully by this weekend. You will have a review. You will also have an updated grades for your class. And you will have the review. And again, the review will be cut off just before the actual exam starts. So it will be due by Wednesday of next week, okay? And that's in a nutshell everything that I have in mind in terms of the administrative staff, unless you guys have any question. So we're going to jump into the or class management. I shouldn't call it really administration, okay? So we're going to move into this chapter. So this chapter deals with rocks and minerals, okay? And that is basically part of the Earth Science that we are supposed to be covering. So this is the first one of the bunch. This is not included in this exam, by the way, the exam that is due on Thursday. So the content that we're covered today and the content that we're going to cover on Tuesday is not part of the exam that is due this coming Thursday, okay? So that is going to be part of the last exam that is going to be done after Thanksgiving, okay? So again, we're going to discuss basically the different rocks and minerals that exist on the Earth's surface. The Earth, basically, think of it as some sort of like a layer structure, like when you look at your onions, for example. It has different layers. You have the atmosphere, which is the uppermost layer, and then you have, of course, the hydrosphere, which is the liquid, basically, layer, and that includes the oceans. That includes also the running water on rivers. That includes also water contained in wells and all of the water. That is part of the hydrosphere. And then, in addition to that, you have the geosphere, which is the one that we're going to be focusing on right now, namely the rocks that exist in it. So the rocks and the minerals that exist in the Earth. The Earth itself, below that, is composed of 3 main layers. You have the crust, which is the upper thin layer that forms the Earth that we see it. And then you have also the mantle, which is a big chunk of the Earth that's below the crust, and that's where a lot of things also happen in terms of the dynamic of the Earth. And then below that, way below that, you have, of course, the core of the Earth, where the iron, and mainly iron actually, is molten, and that is also important for the basically life itself, because it provides one of the main features of the Earth, which is also the magnetic field that protects life on Earth. So this is basically the main structure of the Earth. So you have this layer structure. The innermost is the core, then the second one is the mantle, then the crust, and that's from the below, from the above, basically you have the geosphere, then the hydrosphere, and then the atmosphere. So that's basically how you can think of layers. And of course, there are details in each and every one of them. Today is the focus actually on the structure that deals with the minerals and the rocks that exist, that we see them actually on the mantle itself, and the mantle extends not just in the oceans, but actually below the I mean, not on the continents, but actually extends to the oceans too. To the ocean, basically the bed rock of the oceans, where the water is basically floating, okay, above which is the water exists. So the geosphere is made up of rocks and minerals. This is the focus of today, okay, the geosphere itself. We're going to talk about minerals, and minerals include basically, there is specific definition of what a mineral is, and it has to do with a crystalline structure that we need to identify. Then we're going to talk about the mineral properties. There are some physical properties that we can see in terms of color, in terms of hardness, in terms of basically specific physical properties. And then also there are some chemical properties that are of interest for the minerals. Then we're going to classify rocks basically into different rocks. At least the rocks that we see on the geosphere are divided into 3 groups. Okay. There is a 4th group that we're going to explore down the road when we get into the solar system and planetary systems in general, and those are the primitive rocks, which we're not going to be talking about in this because the Earth, at least the geosphere, does not show those, because the Earth went through a lot of weathering, a lot of basically transformation, that we don't have those initial rocks that formed when the solar system formed. But we'll believe, and actually not believe, actually we'll find primitive rocks in other bodies in the solar system, mainly what you call them? I lost the word now. At least the rocks that did not change from when the solar system formed. Okay. The formation of minerals and rocks, again, that is another topic. What gives the different classifications? We have the igneous, and the rocks that form from the fire, basically. Igneous rocks. So if I try to say it too fast, it's losing it, okay? And you have, of course, the sedimentary rocks, and of course the metamorphic rocks, the ones that go back through the cycle, basically, one or the other, okay? So we're going to talk about how they form and the rock types, the igneous rocks, they're here, sedimentary rocks, metamorphic rocks, and then we're going to talk about the rock cycle. So this is all about the geosphere. This entire chapter is about the geosphere. In terms of composition, when you look at the periodic table, we have so many elements in the periodic table, but actually the geosphere itself, or actually the entire Earth itself, is made up only of few elements, and they are listed in here, okay? So you have 1, 2, 3, 4, 5, 6, 7, and 8. So 8 elements from the periodic table, they represent more than 98% of the entire mass of the Earth. So if you look at the periodic table, the rest, the 100 or so elements, they represent this about 2% of them. By far, iron is the main element, at least in terms of the entire Earth itself, and it's mainly in the core of the Earth. Okay, it's mainly in the core of the Earth, but it also exists in the other layers of the Earth. Okay, in addition to that, the Earth also has a huge amount of oxygen. Okay, then followed by silicon in the periodic table. So those are the main elements so far. And then magnesium, which is an important element. So these 4 basically elements, they form a huge number of the periodic table. So the rest of the Earth, I'm sorry, from the periodic table, what form the Earth. So the Earth is mainly, so if I'm trying to find the density of the Earth, for example, all I have to do is look at the density of these elements, okay? And how they combine, of course, that gives me the overall density of the Earth. And we will find that the Earth has a high density because of this presence of these different materials in it, okay? Earth actually is the densest planet in the solar system, okay? It's not the largest, it's not the most massive, it's not the biggest volume or the smallest volume, but when it comes to density, it's the densest object in the solar system. It's denser than anything else, followed by actually Venus, okay? So that is how the composition of the Earth is, okay? Again, I talked about the different layers of the Earth itself, okay? So you have the core, and the core actually is divided into two divisions. There is the inner core and the outer core, which is a big chunk of the Earth actually inside. And then there is the mantle. The mantle in here is where a lot of convection, basically a lot of motion of the rock is happening, and it's heated rock, okay, from the inside, and that's when it's happening. And then above the mantle is actually where the crust, and just below the crust is where actually the magma forms. And the magma forms with different processes than what actually makes this one hot, okay? So because of how the solar system forms, because of how the planets form, actually, if we go back into history, 4.5 billion years ago, when the Earth came together, it came together from small pieces, okay? Whatever formed basically the entire system, the solar system at that time, and because there was a lot of debris of matter all around, that went into the composition of all of the objects in the solar system, including the sun, by the way, okay? So because of the gravity, matter starts to coalesce and starts to basically come together, and the bigger it is, the more it's going to attract more and more small pieces. So the initial collisions and gravity work together to basically bring parts together. Now, these objects are due to collision. So when two objects collide, they produce a lot of heat. That's part of the conservation of energy. The lost kinetic energy, where did it go? It goes, among other things, to heat, okay? And so if you're wondering about what happened to sound, that's in vacuum, so there is no sound formation at the time. So it's really going to, yes, there is debris that's going to fly out, but mostly if the two objects come together, that's when they're going to go it's converted to heat, so they heat up, okay? Now, when there is a big chunk enough of it, now the Earth starts, or the planetesimals at that time, they're not still Earth or planets at all. They're smaller pieces of a chunk of basically rock. The gravity now starts to work together. One of the things that gravity does is brings more materials closer to it until they fall on it. So gravity now, because of gravity, is going to also convert that potential gravitational energy also into heat. So now you have two sources of heat. The piece starts to grow, gravity starts to actually shape the ball into a spherical shape as the mass becomes bigger and bigger. And now, the heavier, because super hot at that time, there is a deposition of the heavy elements toward the lower place, just like, for example, when we did the buoyancy, when we were talking about the density and things like that. So the materials that are denser, they fall to the bottom. The material that are lighter stay to the top. That's why the core itself is made out of iron, because iron is super dense, relatively speaking, for example, when you compare it to oxygen and other compounds, okay? So that is how the solar system, how the planets basically formed, and it got its current structure. Obviously, there is a third source of heat in here, and that is radioactivity, and that's what really kept the Earth also warm for a long time, because it has a lot of radioactive materials. So radioactivity is the third source of heat. So you have the first one, which was really due to collision, which is collision heating. You have another one that is due to gravity, which is gravity pulling matters to it, converting gravitational potential energy into heat. So that's another source of heat. And the third one that is actually due to nuclear processes that basically ejects matter, and also due to radioactive materials, and that also generates heat. So that's how basically the core is super hot. And that is why it's melted, actually, because of these three processes. Okay? The Earth itself initially was super hot, and because of that, the density basically started to shift around. So the lighter materials, or at least the less dense materials, stay afloat, stay to the top, and the denser materials fall to the ground. Just similar to how you take, for example, oil and water, and you mix them together, but after a while, you'll see that there is a clear separation, because water is more dense than oil. Water will sink to the bottom, and oil will stay to the top. And that's basically how that forms. Okay, leads to some beautiful pictures. When you have rain, for example, that falls on this asphalt, and the oil from the asphalt rises to the top, that reflections give you all kinds of different kind of different colors that reflect from the light and all of that. So that is similar to that. That is how the process works, and it has to do with the density. Okay. I know some of you have joined us, and since you guys just came in, you don't expect to go back and watch the videos later on. So, and you're entitled to the first announcements that the few people who started with me earlier in the class, and the fact that there will be an exam a week from today, okay, Thursday, and that is exam 3, covering chapters all the way to 19, I think 12 to 19. And this chapter is not included in the exam, in the exam 3, okay? There will be a review that is going to be published this week. It's going to be due before the exam, so that you guys are ready for it. And also some of the grades will be updated by this weekend. Okay, so that's in a nutshell what you guys have missed. And as I said before, you just came in, and you might think that you're not going to be watching this recording later, so you might miss on this information. For the late arrivals, does this make sense to you guys too? Just want to confirm that you have a full understanding of what's at stake. Okay, good. So let's continue with this. So this chapter is not part of the exam, by the way. It's part of the last exam that is going to happen after Thanksgiving. So the crust itself also, now because of this, yes, iron is the main component of the earth, but mostly it's sunk to the, basically to the core. Now the crust itself, as we described earlier, that the crust is a thin layer that is on the top of everything in here, and it extends only several kilometers versus the others that extends thousands of kilometers. Then it's made up mainly of the lighter objects, which are mainly oxygen and silicon, which they form the silicates, because silicon never really occurs by itself. It's always in a composition of some sort with the oxygen. Okay, so these are the silicates, and silicates now they can combine with other materials in here. So this is basically the composition that you have on the Earth crust itself. So this is basically the upper surface itself in here. Okay, so the Earth's surface is oxygen and silicon make up mainly about 75%, and the rest are the other elements. Iron is still there. Iron is everywhere in the Earth. Okay, so it's not all of it in the core, and that's what gives basically. That's when we extract it. We get a lot of minerals from that we use in the industry. We use aluminum for cans, for example, iron for steel, for cars, for everything else that we needed. Calcium actually, and its structures are used actually in other stuff, like for example buildings and so on and so forth. So you have other minerals in here, sodium and potassium and magnesium, which are important also in the industry. And those again, 1, 2, 3, 4, 5, 6, 7, 8, and the rest is very, very small chunk. Okay. So by far, these are the two main ones. In addition, when you add to them aluminum and iron to some extent, and calcium if you wish, you have accounted for the most of the part of the crust, the thin layer that we are actually called Earth on a day-to-day basis. Okay, Earth for the most part is super hot planet, but we live on a very thin, not too hot part of it. Okay. So minerals, they are naturally occurred, formed naturally rather than manufactured. So that's by definition what a mineral is. Okay, they are crystalline in structure. In other words, they have regular shapes. Okay, I took a picture earlier of the salt, but they couldn't upload it yet, and it has to wait for a long time before it goes online on my online drive. So I don't have it ready for it there yet, but it's nice to go and look at the salt with a magnifying glass. So take your phone and zoom on it, and you will see the crystalline structure. You see distinct shapes in here, and this is one of the things that fascinates people when they look at shapes, because that's one of the things that attracts basically beauty in it. But also it's the main reason, or it's one of the main reasons for the physical properties of materials. So that's really That's really something that we have to pay close attention to, is the crystalline structure, whether or not it has a crystalline structure or not. Like, for example, the fact that it's solid doesn't mean that it is a crystalline structure. For example, take the glass in case, it does not have regular basically position for the atom. So it's like it's called an amorphous state, which is really like a liquid. Okay, so that's the glass, albeit it's solid in that in room temperature. Okay, versus crystals, like for example salt, which has a definite crystalline structure, and the crystals, they have all kinds of different configurations. That is basically what gives us some properties, which we're going to talk about it. Okay, so the atoms, ions, or molecules have a specific arrangement, and that arrangement is orderly, is repetitive. It repeats itself. Okay, so that is what we mean by crystalline structures. Okay, they have specific chemical composition. Okay, and they are generally not organic. Okay. Is a new branch of industry where they're looking for crystalline structure for organic matter, but they're not, again, that's not, that's synthetic, okay? So, again, when we talk about minerals on Earth, we talk about the fact that they are not produced by organic matter, okay? So, again, minerals are classified by their chemical properties, and namely composition, because how they are composed. Like, for example, salt, everyday salt is NaCl, sodium chloride, so that's the chemical composition. And the crystalline structure, again, there are different kinds of geometries that you can have in here. You can have cube, where each element sits on basically the vertices of the cube. The cube has 1, 2, 3, 4 basically points in it. And you have, in this case, a cubic crystal. But then what you can do, you can have, in the middle of that cube, you can have an atom of a different atom. Oh man, in this case, it's a cubic. Yes, it's a cubic, but it's centered. But there is a different crystalline structure where you can still have a cube, but instead of the other atom sitting in the center of the cube, you can have it sitting on the faces. And there are 6 faces on the cube. So in this case, you have cubic, what is it, face-centered or structure. And then you don't really have just a cube. You can have a different arrangement. You can have actually, what is it, 6 shapes. What is it called? Forgot the name for it too now. So you can have different geometries on how the atoms rearrange themselves. And if you ever walked into a chemistry lab, you will see them on top of the shelves, okay? Different kinds of crystalline structures with different basically spherical objects in there representing different atoms, and you can see the crystalline structure in that case. Okay. Obviously, this is not necessarily chemistry, but that's actually in material science, and it's usually in minerals. Basically, in Department of Geology, you see that too, and solid state physics labs also you see that too, because that's an important properties of minerals in general. Okay. Some of the properties of minerals are first of all, the crystalline form, the form itself, the one I was describing. The hardness, in other words, how easy is it? Can you scratch things with it? Okay? Can you take, for example, a piece of iron, okay, and scratch another piece of different kinds of material, okay? So how easily the other one scratches, that's basically what we mean by hardness in here. And if we look at the scale, actually the hardest material in terms of this, it's not how easy it breaks. That's not the point. It's how easy to scratch off, okay, other elements. You will see that actually diamond is the hardest material in this case, okay? And nails happen to be also on that scale too, okay? So you can, although nails are not crystalline structure, actually they are organic matter, but the point in here is the hardness that scales into how much surface is scratched from another surface, okay? Cleavage and fracture, there are 2 different ways. If you take a material and you hit it with a hammer, for example, there are several ways it's going to break. Either going to break into 2 pieces where there is a sharp line in here, and that is what we mean by cleavage in this case. The cleavage in here is the separation along a planar structure, because the material itself is rigid or has strong chemical bonds on a specific plane. but they're weak bonds on between this two different planes. So when it's struck in this case, it's easy for it to break along the planar lines than along the different inside the planes themselves. So that's what we mean by cleavage. But the fracture in this case is the other way around. Okay, is when it breaks into different pieces, and even then it's classified into different ways of different ways of breaking it. Material resistance is one of the key elements in a lot of laboratories, actually, especially, for example, if you are in a civil engineering lab, because you would want to build a building with the material that is the most resistant to, for example, weather, that is the most resistant to stress, that is the lightest material. You don't want it to be too heavy, okay? And you don't want it to be too expensive. So you do all kinds of research and different basically studies and comparisons in different compositions involving chemistry and physics, of course, trying to come up with the best material that you can build your building, whether it's a building, whether it's a car, whether it's anything, okay? So you, for example, you're trying to build a shuttle. So that's one of the materials you want. You want it super light, super resistant. If you're traveling at super great speeds, you don't want with the next flying object coming from an asteroid or something, it's going to hit your planet, your rock, and then break it and shatter it. So there is all kinds of properties. In addition to that, of course, you're considering the cost too. So that is one of the things, and that's why minerals exist in nature, and also they are made in laboratory. On all the time, we make up new materials that meet certain requirements. So these are one of the requirements. The hardness, for example, the resistance to breakage, or why they break, and how they break, and where they break. That is important. So you apply stresses on it, like, for example, hammer it, or twist it, or pull it, or compress it, and then see what happened, okay? Or shear it, okay? You take an element, for example, and you put it from one side and not the other, okay? So the resistance to shearing also is important too. So it's sitting still on one side, but you're trying to pull it on one or the other. So those are the type of the properties. Of course, color is another property of materials. Different materials have different colors, and we want to identify them too. The thing with color is that it's not really sometimes, depending on the impurities in the metal, they may or may not, they may have different colors. So you have to be careful with color. The fact that it's a golden color doesn't mean that you have gold, and that's one of the things that was really a problem in the early days for the people who hunt for it. So you have other indicators other than color, depending on basically what you have in there. Okay. And then density. Density is actually a useful also way of measuring identifying the mineral that you have in place in there, because you can take advantage of it, for example, in doing in separating different materials based on their mass. Because if you have for example, in the early days, on how they used to find gold, is they use the same thing. They take advantage of the fact that gold is super dense material. It has a density which is 19 point something grams per cubic centimeter. So if you have it mixed with other materials, for example, dirt and other rocks in from the ore that you take from the mountain or the riverbed or wherever you are, you put it on with a little bit of liquid, and you start shaking. Okay. Obviously, the denser the material, the more resistance is going to go to it. So it has more inertia in this case, so it's going to stay on the bottom, and the ones that are lighter starts to move to the top. Separate those, do more, separate those, do more, till at the end you will end up with the densest material on the bottom, and you look for it, and most likely, if you are in a place where that's rich in gold, that's where you have struck gold. Okay. So density is an important property too, and different minerals come with different densities. Okay, so it's important. Aluminum, for example, is super light material, but if you compare it to, super less dense material, if you compare it, relatively speaking, for example, with iron, which is far more denser than it by almost a factor of 2.5 times. Copper is even denser than iron. Okay, and that's how you go all the way to gold, for example, which is super dense material. Okay, so density is actually an important property that tells me also into the type of materials that you have. Now, it's very important also for us when we explore astronomy later on to try to see what the densities of different planets are, or different objects are, because it tells me also on the composition of that object. For example, when you look at the density of the moon versus the density of the Earth, the density of the moon is a lot less than that of the Earth, and I know the moon does not have a lot of iron compared to the Earth. That's because Earth is a lot denser than it. If you look, for example, into the density of Jupiter, for example, or the density, for example, of Saturn, which is a different planet, density of Saturn is less than 1. So it's less dense than water itself, okay? So actually Saturn, if you put it on an ocean, if we can find an ocean big enough to put it on, because it's much bigger than Earth, by the way, it's going to float because it's less dense than water. So it tells me then that Saturn does not have a lot of minerals. It's mainly gas, basically. So that's how density has a lot of important applications, not just in minerals in here, but it's also for other places too. Okay. So crystallization is the formation and growth of solid from a liquid or gas. So basically, there are different processes through which atoms start to deposit on one another. And if they're basically, they have specific, again, chemical properties that give them the ability to bond together, then they can form the specific crystals depending on the material that you have, depending on the chemical composition that they are supposed to have, okay? Again, and they start to arrange themselves, and the process involves, of course, temperature and other processes. Once the crystal forms, then it's going to repeat until you have the crystalline form, crystalline shape, basically, have developed from it. Again, it depends on the internal atomic arrangement. It's determined by the atoms of the ion size and packing. That's why sometimes there is room in between, like I was talking earlier. You have a cube that has 8 nodes or 8 vortices, okay? Depending on the size of those, if there is room in the middle, then you can have actually a centered cubic crystal. If they're too dense and close from one another, then you can't, okay? Like, for example, in the case of carbon, they're small, and when you put them next to one another, they start to pack in different configurations. Now, there is one way for carbon to give you a graphite, which has a different physical properties than, for example, the same chemical composition, which is carbon still, but it's super packed, okay, together, that they don't leave any room for between them and anything else. Then at that point, actually you have the same chemical composition, but you end up with a different crystalline structure, and in that case you end up with diamond, okay, which has the highest hardness that we know of. So same chemical compositions depending on the process with which they form, temperature, pressure, and the space where they can move around, then you end up with different actually crystalline structures. Okay, here is the example of diamond and graphite. Both of them are carbon, basically. Both of them have the same thing. One of them, the hardness is super high because, again, there is no room between them, and they are actually, so the carbons, they are super packed in this case. The carbon atoms in the graphite, they have this layer structure in them, and when you rub them against any surface, and especially paper, for example, they leave a mark in there because those layers start to peel, okay? And that's why you use them in pencil. So the pencil is a good example of, I don't have any pencils in here, is a good example of a graphite. That's actually the material that formed that. So it's the same thing as diamond, okay? But they have different crystalline structures because, again, now here in the spacing, the way the pressure was exerted to form this one is not the same as that one. Again, I talked about the hardness is the resistance to scratching. Hardness is dependent on the strength of a mineral chemical bonds. Bond strength is determined by ionic, basically, bonding. And the Mohs scale compares the hardness of different materials. Okay, I mentioned briefly that the hardest material in this case, it goes from 0 actually to all the way to 10, and 10 being the hardest material, namely in this case diamond. Okay, so you take diamond for example, and you rub it against a different material, or you rub it against material, and see how much basically that material is scratched. You compare it to another material and see the two, which one is leaves less scratches than the other, and you rate them basically depending on the materials. So this is an empirical scale. Okay, just like for example the seismic the earthquakes. Gold, for example, is a soft mineral. It's very easy to scratch. Okay, because its atoms are very tightly packed. Its atoms are large. Its atoms are tightly bound. It has a very high melting point. No, okay, because they are very large and they are very easily movable from the material. Okay, I talked also about another kind of properties. So that's one property that we talked about, namely the hardness. The second one is the cleavage and the fracture. Again, the cleavage is the planes have a weak bonding between one another, so it's very easy when you break the material into basically what looks like a complete basically surface in here on both sides. Okay, because there is weak bonding. But for fracture, there is actually the same bonding for all the planes. So when you hit it, it's going to form, it's going to break basically and shatter into different pieces. Again, color is an obvious feature. This is basically of different materials. Sometimes, depending on the impurities, color can change. Case in point in here, ruby and sapphire. Okay, they give different colors based on what's in them. Okay. Density is the ratio of the mineral mass to its volume. In simple terms, it is how heavy a mineral feels for its volume. This is a poor definition. Okay. This is not a good definition. So I really want to go back to the basics. So you take the mass of the object and you divide it by volume. Unit volume. This is the density. Okay, so it's not how heavy. Yeah, for its size. Yeah, if you have defined the unique size. Okay, if you say okay, from now on I'm dealing with 1 centimeter cubed. Okay, and what I mean by size is the volume actually, unique volume. Let's say for example it's 1 cubic centimeter. Then you can compare its mass, and if you are on Earth, you're allowed to use the word heavy. Okay, so that's basically how the definition is. So, what is density? I'm just following the recommendation of Sarah and writing the question in here. So what's the answer to that? Anybody? Are you guys with me, or am I alone in here? Okay. So any takers then? Okay. The weight of an object based on its mass, that's not what I was looking for, honestly. The ratio of mineral.
Is it a degree of compactness of a substance?
That is to some extent, yes. You can say that. That's good. You can use that terminology. But there is a way of measuring it that Josh hit it on the nail. Okay? But except that Josh basically described for mineral, but this applies to everything. Does this make sense? Okay, basically, it's the ratio of the mass over the volume of any substance. It's not just for minerals. Is this better now, Sherry? Okay, good. And also, how Christina is the one who intervened earlier. Is it? That's also another way of saying it, except that's too fancy. Yes, yes, sir. And the volume. Sherry, does that answer your question? Yes, I did already. I did type the question, but I really don't want to type the answer. I want you guys to put it in your own words, especially I like the way that Christina put it. Good? Did you see the question? Okay, very good.
Yeah,
Okay.
I got all of that, but I don't understand it.
Okay,
Even when you said the answer, I don't understand it.
the question is, what is basically the density? The density is the ratio of how much mass per unit volume. Okay, that's how Emmanuel put it. Christina put it into basically the level of compactness of the material itself. Okay?
Yep.
Okay, very good. So, and again, it's a good indicator of this materials, whether we're talking minerals or anything else, okay? Okay, one of the things, and I think really I want to go back to this density in here, is the reason why it's important because it doesn't depend on how much matter you have. You can have a very small of it, or you can have a ton of it, or you can have the entire planet of it, or the entire solar system of it. The density never changes of a specific material. That's why it's important. If you have a small fraction, you know that you have this material no matter what, okay? If you have this much of it, and you measure its density, it's the same number. So it's really a property that doesn't depend on how much stuff you have of it, okay? That's really an important property that is actually needs to be tied up to it. Does this make sense to you, everybody? It's called an intrinsic property. Okay. Okay, when we talk about physical properties of a material, they are related to the external conditions of temperature, pressure, and amount of space available for growth. Materials, they don't care where you put them, okay? Whether you put them in a confined space or you put them in a different space, they are physical properties, they are physical properties. So the correct answer is not A for sure. As it, so if we say A is not, then D is not. So we excluded both, okay, in the same process. How about C? Crystal form, hardness, cleavage, and fracture and density. Those are actually the some of the physical properties, okay? So it's the chemical composition, basically what they made up, okay, and how they're arranged. That's what dictates their physical properties, okay? Color is mainly related to the chemical composition, but again, it may change because the chemical composition may have changed because you have more impurities of one material to the other, not to its internal arrangement. Again, there are two types two classification of minerals that we found on the surface of the Earth, on the geosphere, and they are mainly involved because remember the main components in the crust are silicon and oxygen. So these are silicates. So you have the ones that involve these two and the ones that don't involve them. Either silicates, and silicate minerals include, they must have a silicon and oxygen in them. And non-silicate minerals, they don't include that. So silicate minerals make up the vast majority because of the fact that you have silicon and oxygen are the main components in the crust itself. So those are the two types. The vast majority are silicates. So if somebody asks you what is the main composition of the Earth's surface, it's silicate materials, okay? Silicate minerals. Now, non-silicate minerals, they're basically anything else. Pure, for example, gold or pure iron or whatever that other things that you have them, okay? So you have different kinds of materials, okay? So silicate minerals are made up of silicon and oxygen atoms along with other minerals, along with other elements, okay? Aluminum, magnesium, iron, what is this? Manganese and tin. Is this the? And then, so the silicate mineral have the same fundamental structure, and they all have this tetrahedron crystalline structure. Basically, you have four atoms on the corners, and then you have the middle one. So this is not a cubic structure at all. So this is a diamond structure, or a polygon based. What is it? It's a three-dimensional object. I'm trying to do it with my hand. It's in here, okay? So it's kind of difficult to do, okay? But that's the one of the crystals. Crystals they come up with different shapes and different forms, so it's not just cubic structure, okay? And then silicate minerals themselves, they can either have magnesium in them or iron. So in this case, they're called ferromagnesian silicates, and non-ferromagnesian silicates are the others that don't have iron and magnesium in them, okay? Remember, iron and magnesium are one of the main components of the crust too. Because iron and magnesium are denser, especially iron is super dense, then in this case, they will, the materials, the ferromagnesians, they will be denser than non-ferromagnesian silicates. So that's one of the, because of the composition. Non-silicates, they include carbonate materials like calcites and dolomites, and those are the ones that are used in constructions and materials that make up basically cement and other things in here. Okay. The oxide minerals, those are the ores, okay. And then the sulfides, sulfate minerals. I think this is the one that is used for the casters and all of the things, the plaster that you use in the construction also. And then halide minerals, and those include salt. This is everyday salt, okay, and fluorite. And then you have native minerals like gold and platinum and iron and all of those things. Again, they don't include any kind of silicon and oxygen in them. So they have calcium in them and other minerals in them, combined together with other stuff, including iron, pure materials, pure iron, pure minerals. Okay, there is a nice table I didn't share with you guys, but I think it's a good idea to look at it, and it divides basically the different materials on the surface of the Earth and how they are. You have silicates on one side and non-silicates on the other side. Silicates, again, they are different depending on they have magnesium and iron in them or not. And then non-silicates, they have all kinds of divisions in them, including pure minerals. Okay, pure elements, I should say. Okay, in their mineral form. So there are different ways. Basically, minerals formed by the process of crystallization because they are crystals, remember? Okay, minerals crystallize from two primary sources, magma or water solutions. So you have the hot rock, the molten rock. When it starts to cool down, depending on the melting point of the different composition of the magma, in this case, it's going to have deposition. Okay, the ones that melt at the highest temperature start to form crystals first, and the ones that have less and less melting points they start to come after that until you have at the end the entire magma. When it cools down, you have different structure. And so the ones that have a, depending on the melting point, the water deposition in this, or the water solutions in this case, again, depending on how much water it has in it. For example, when you have running water going through the mountains or through the rock, it's going to grab with it calcium and other minerals. And when it starts to dip, for example, in the caves, it's going to start to deposit because there is an evaporation in this case. So each time when a certain amount of a drop of water falls, then in this case it's going to leave behind the mineral, and the water escapes until they form nicely in the caves and other places in there. So this is one way, for example, of how crystals form. Again, I explained in terms of the magma part of it, and it has to do with the melting point, because silica in this case has lower melting point than other minerals. So the rich mineral starts to deposit first, and then the composition of the silica starts to increase until you have those. Toward the end, when you have the forms at the end, you have the silicates, which is the thinner layers on top of the crust, for example. The water solutions, I also explained the fact that actually there is another one also that occurs actually during the magma, because the magma contains small amount of water, and water, when it's super hot, it's going taking with it actually minerals, that have dissolved in the water, and as it starts to cool down, those minerals start to deposit in the cavities of where that basically molten rock is cooling down. So, and they precipitate because you have, in this case, the water is evaporating. Okay, and then it depends also on how that forms on the solubility, and that's how salt actually is made. Actually, in the old days with the basically lakes. So in this case, you have a super salty water. The calcium and other deposits deposit first because of the solution. The solubility of those are less than that of for example, pure salt. Until at the end, the last one is salt. So when the last amounts of water, in this case, evaporate, the salt then is going to sit on the top of the layer in this case. So again, that's another way for the crystals to form, because as the atoms are basically coming down from the sodium and chloride, starting to basically dissolve from the water because the evaporating water, the atoms start to deposit one by one, forming the salt in this case. Okay. Rock types, I'm looking at the watch also in here. So we have three main rock types on the Earth itself. Actually, there is a fourth one that we're going to explore down the road. So the igneous rocks, they are the ones that form basically by through crystallization process by the cooling of either magma or lava. And there is a little bit of distinction that we have to make in here in this case. You have volcanic rocks that form through the eruption of basically volcanoes. And you have a lava that flows on the surface in this case, and also that goes down and forms crystals, and those crystals, they form the igneous rocks. Sedimentary rocks also, after the rock starts to deposit in this case, and they start to compress on one another, they form different layers in this case, and they are the so-called sedimentary layers. Usually this is subject to a weathering phenomenon, basically due to wind, ice, and water flow, and other phenomena basically that brings them together, and they start to compress. So more and more deposits you have on top of one another until now a nice layer starts to form. Okay. Metamorphic rock is formed either from one of these three sources, whether it's igneous rock, changing form basically due to pressure and temperature, or sedimentary, again rocks, again due to pressure and temperature, and also weathering, it can be changed. And metamorphic rocks also changing again. Okay, so those are the three sources for metamorphic rocks. Okay, so igneous rocks, they're molten rock. That's what the magma is. That forms inside the earth. Okay, and so source for it is really the process of because you have to think of, for example, of why ice melts. or why water, for example, boils, and the only reason why it boils is you reach the phase transformation temperature of around 100 degrees Celsius. But that really works only on the surface of the sea level. If you go higher and higher, if you change pressure, for example, and pressure is different, then at a higher pressure, you need really a higher temperature for the water to boil. Okay, so you really have to be careful in here for the boiling points in here for water. So it has to be on the surface. Same thing in here in the rock. If it's under tremendous amount of pressure, then the temperature rises, and it rises because of those different higher. Actually, the higher you go or the lower you go in the surface of the earth, below the earth, the temperature rises automatically to a point that it becomes too hot for the rocks to melt. But they will or will not melt depending on how much pressure there is, depending on how much they're above them. So if the pressure is too high, in this case, they don't melt. But in other regions, their pressure is not too high enough, and the rock actually melts, and that's where the magma forms. Now, when this magma forms, you have crystalline structure that starts to form, okay? So lava is molten rock, magma erupted at the surface earth. So that's basically, if you have ever seen the picture of Hawaii, how those basically flow of the magma, that is exactly what we talk about. Okay. Again, I mentioned the fact that the temperature increases by about 30 degrees actually per kilometer. Okay. Rocks in the lower crust and upper mantle are near their melting point. Any additional heat from rock descending to the surface may help to induce melting. Okay. Heat is a minor player in this case. The heat that is coming from the earth is really not that big of a player. So it's really the motion in here that plays a major role in the formation of the magma. And it's not because the earth is super hot inside that forms the magma. That is a different process, okay? That has come from the early formation of the earth, plus the radioactive materials that are actually inside the earth. Again, a role of pressure, lower pressure lowers the melting point of rock, okay? Higher pressure increases the melting point of rock. When confined pressure drops, decomposing materials melt, okay? Decompressing materials melt, okay? Still have a few minutes. We still have a lot of rocks. So let me just go through quickly in here. I expect you guys to go through these materials. Again, they are not part of this exam. They are part of the next exam. And you will have a quiz on this one, but after the exam, after exam 3, you will have a quiz on this chapter. So that's part of the things that we will have down the road, okay? Again, we're talking just on the process of how the magma forms. And then how the crystallization now, because of the fact that now the magma is cooling down in contact with the air, that is usually less temperature. So as it cools down, the materials with the higher points, higher melting points start to basically melt first and form crystals first, and then the next ones, and so on and so forth, until the entire basically magma solidifies and basically creates minerals for us. So there are 3 types basically of magma rocks, if you wish, crystalline structure that form from magma, the basaltic structure, which is really, and then you have the andesitic, which is really related to the Andes, and then they have the granite, which is another form of magma in this case. You have the ones that form below the surface of the earth. You have, this is called the intrusive or plutonic rocks. And then the ones that form because of the material that are actually ejected during volcanoes, for example, they're extrusive as opposed to intrusive, or volcanic rocks. Okay, here are examples of them. Again, there are the ones that form under the surface of the earth. So the magma cools down and forms the ones that are intrusive. And then the ones that form above, and those are the extrusive. Okay, you have lava flow and volcanic rocks. Sedimentary rocks, basically, they are due on the different weathering phenomenon. Weathering basically has to do with the effects of wind, ice, water, and so basically that's what we mean by weathering. Erosion is actually the transportation of a rock from one location to the other, usually by means of water or wind or other factors. Deposition is the process when they start to basically rest and come to a stop, and that's where the process with which they come together. And then sedimentation, as this layer starts to deposit on one of the other, that's when the rock starts to form, or the sedimentary rocks start to form. So you have, think about it, you have a rock that was already formed from the, for example, igneous rock, then you're going to take it through different processes, and then it's going to change to a different form. So the weathering in this case can involve the mechanical processes, namely physical processes, and that is the breaking and disintegration of rocks into small pieces, and chemical processes where actually the chemicals are decomposed into their to different chemicals. Okay, usually water is involved in here. And there is actually different weathering phenomenon, which is biological activity, what bacteria does in this case, and starts to, or a plant, for example, grows in between the rocks and move them apart and break them apart. So the most important agent in this case is water. There is wind also that has for example, for the mountains. The erosion, I just mentioned the fact that this is the removal of material from what they formed by either water, wind, ice, or gravity, actually, too. That plays a role, too. Okay. Erosion does not occur in place. It involves movement. Okay. You have different levels of deposition in this case, whether or not it's sorted or poorly sorted, as you can clearly see from the size of these rocks in here as compared to the same item in here. And this is the sorted, where you have basically the shapes and the colors, and they are basically uniformly distributed. In here it's not. Lithification is basically the formation of rocks, and that's when this materials that become rocks. And compaction or cementation, that's when they basically become a rock now together, all of them. So the weight in here presses together, or the compaction releases of pore water rich in dissolved minerals. That also creates the new rock. So there are different kinds of sediments and sedimentary rocks in here. Shale, which is mud-sized particles and thin layers, sandstone. Those are all basically different kinds of sedimentary rocks. I'm looking at the watch quickly in here to see if we can get into the metamorphic rocks, which is another kind of rocks, the third kind. So there are three kinds, and that's the question. What are the main types of rocks on Earth's mantle or Earth's surface? There are three of them. And they are, any help? Anybody? Can you look at your notes? Anybody? Igneous, the one that's formed from from fire, sedimentary, and metamorphic. So Josh summarized them all. Okay. Very good, Emmanuel. Okay. So those are the three types. Okay. Usually they are listed in this order into the way how they form. Igneous first, sedimentary second, and metamorphic, which is the transformation of the other two, plus the metamorphic, so all three into new rocks. Okay. So that's the second question of the day. You guys are keeping track of these things. So again, metamorphic rocks are produced from igneous rocks, sedimentary rocks, or other metamorphic rocks, basically also form new ones. Okay, metamorphism occurs via recrystallization and mechanical deformation. Okay, usually there is other elements in here, heat and other stuff that is involved to basically reform the crystals and come up with a different, basically, material. Okay, different rock, I should say. Okay. The alteration of rock by both heat and pressure over an entire region rather than just near a contact point between the rock bodies. So that's the regional metamorphism. Metamorphism is basically the change, okay? And then you have the classification of foliated and non-foliated, basically layered, when sheets are not layered. And if you look at it, this one in here, some of them have non-layered, and some of them actually there is a more or less a layer, but there is actually a motion in here. It seems like at some point these layers, after they form, they deform somehow. That there is another one in here that involved this, for example, deformation here. You can clearly see it. So this is a telltale sign of the activity. So if you look at rocks, for example, at least if you go to the Grand Canyon and you see the different things in here, so you can clearly see the sediments in here, how they formed and when they formed, and if there was an activity at some point that caused the shift in the structure. Okay, I think we're almost done with this in here. So again, okay, the rock cycle, which is an important part of the whole process. So the molten rock rises from the depth, cools, solidifies, and eventually returns to the magma when it forms, okay? Because as the new deposits comes onto the place, so basically the magma forms the rock is moved, transformed, changed, and now it's deposited. Another layer comes on top of it, and another layer comes on top of it, until this layer now becomes on the bottom and becomes in contact with the magma again, and then it's taken back again to the surface of the earth to be on the top until the whole thing is basically in a cyclic motion. So that's how the rock cycle is. So the same rock that you're looking at it today, of course, you have to wait for it in geological times. This is not going to happen tomorrow for sure. Okay, it's going to take the same amount of time to find out who won the elections, I guess, because it's taking forever now. I'm sorry, I had to throw that in. Okay, okay. So it seems like we have to wait forever to know who's going to be our president. Anyway, so basically the rock will move onto the top at some point and then comes down. That's why the fourth type, we did not mention it in the case of the earth because we don't have it. So, and these are the so-called primitive rocks. So we get them through the meteorites actually. That's when they land on the earth. So those are the initial rocks that form the solar system. That's why they're so precious, because they're so valuable. They tell us exactly how the solar system formed. They tell us history, basically, of what happened in the beginning. But now the Earth itself is always basically changing its rocks, so we have only these three types. So again, the magma, it doesn't matter where you start, okay, because this is a cycle. So the magma, molten rock, cools down and solidifies and forms igneous rocks. Igneous rocks form sediments later on. Sediments later on will melt, okay, to form basically metamorphic and change because of heat and pressure. And then metamorphic then rocks at the end will turn back into basically when they're becoming in contact with the magma, they're actually going to turn into magma, and so the whole process basically goes into a cycle. Okay, the metamorphic rocks is not a single process. Okay, there's several processes. It may even involve metamorphism of already the metamorphic rock that has formed a long time ago. So this is in a nutshell basically this chapter. Okay, hopefully you guys are basically on top of these things. I'm hoping that you guys will be ready for the exam 3, which would be a week from today. Okay. And then also ready to, if you, I'm going to have to shoot for Friday evening, okay, for the, because and today we have a meetings, and then hopefully in the afternoon on Friday your review should be ready for you guys so that you can get ready for it, okay? I mean, I enjoy teaching. I really don't enjoy anything else. So teaching and playing soccer. Any questions?
So like 2 questions for today, correct? Or
Why is my volume low? Excuse me, let me see. I can't, probably from my end.
Is this any better or nah?
I have it at max, okay? I can't really do better than this. Go ahead. Maybe I can, go ahead.
Oh, I was just asking, so there's only like for 2 questions for today, right? Gotcha. Okay.
I think so.
Thank you.
Okay. I see you guys a week from today. It's going to be chapter 21, okay? And again, that's not part of the exam. And watch for the review by Friday evening.
Mm-hmm.
Bye.